So periodic table, I would say that it is one of the biggest achievements of human mind, or the one of the best creations that humans have come up with, like Mona Lisa or David by Michelangelo or Pyramids of Giza probably. And this is right up there. It is that great an achievement, that amazing feat. Now, what exactly is this thing and why does it have such a weird structure? So let's just look at this. What do we see? We have four blocks here. So we see four different things. So there you go. That is the four blocks that you have. On the left side, you have the pink one. So just ignore the different circles and all that that you see. So on the left side, the pink one, that is one block. Then you have the green ones right on the right side, like the other extreme. Then you have these green ones in the middle, and then these blue ones or purple or whatever color you want to call it, these over here. So what exactly is the structure here? So we divide all the elements. So the first word that you need to know about is element. What exactly is an element? It is anything that has a single or a certain kind of atom in there. So all the atoms of one element have this are of same kind. What does that mean of same kind? It means that they have just the same number of protons, because in atomic structure we saw that number of protons defines an atom. So over here, the number of protons is what defines what an atom is, and all the atoms in that have the same number of protons, we call them that they make an element. So far we have 118 different elements that we know of. That means 118 different kinds or different varieties of atoms or proton numbers that you have. And that is how we arrange the elements. So in periodic table, you won't find compounds. You won't find methane or water, because those are not elements. Those are compounds. So over here, you'll find hydrogen or magnesium or iron or palladium or potassium or things like that. And that is because they are unique elements that their atoms have a certain number of protons and no other atom has that. Sure, there are some that we value more, like gold or platinum. We value those kind of atoms more than, I don't know, oxygen. Although there might come a time, I hope it doesn't, that oxygen might be the most expensive thing on the planet because you need it. All right. So we have four blocks here, the left ones, the very right ones, and these two in the middle, the blue ones and the green ones. Together, these blue ones and the green ones, we call them transition metals. You will notice that it says SPDF. You don't need to know that for O levels or IGCSE, you don't. So we have this one on the left side. These are, you can say that these are soft metals, these ones over here, except for hydrogen and helium. The rest of them, we can call them soft metals. And these are transition metals. These are more traditional kind of metals that you have. And over here, you have a mixture. You have some non-metals, you have metalloids, and you also have some metals in there. So for example, over here, you can see lead all the way over here, which is a metal. Similarly, you can see carbon there, that is a non-metal, okay? And then you can also see arsenic or silicon, which is a metalloid. They are metals that act, non-metals that act like metals. So this over here, lead, thallium, flerovium, these are metals. And then you have silicon or arsenic. These are metalloids. And then you have pure non-metals like carbon or fluorine or chlorine or neon and argon and all that. So we have that kind of arrangement over here. All right, what's next? We also arrange them based on their proton number. So you'll notice the number on the right side, top left, that number is the proton number. So it has 2 of them. Over here, this has 7 of them. This has 9 of them. This has 652. This is 112. What are these things? These are basically proton numbers, the top left one, as you notice. And you will notice that I'm saying 1, 2, 3, 4, 5, 6, 7, 8. They're all in an order from left to right and top to down. They're all in this order of proton number. Interestingly, when people actually made the uh, periodic table in the first like 1800s, he was a professor in Moscow, Dmitry Mendeleev. When he made it, he arranged them based on the atomic mass. Now we don't have do that. We use the proton number because now we know that different atoms can have different masses, but they can have the same proton number. So for example, over here, if I put my arrow on oxygen, you'll notice that it says 15.999. What does that mean? That means that this is the average mass of oxygen. By average mass, I mean that this is oxygen with all the different isotopes of it and the abundances that those isotopes have in nature. And this is the mass, the relative mass that oxygen gets because of that. Similarly, if you notice that chlorine has 35.45. In O levels or IGCSE, we usually call it 35.5, which means that it has an average mass of 35.5. So if you pick any of those, that is the arrangement that you have. Similarly, you'll notice that you see on the left side, the bigger square, 287. Those numbers are the electronic configuration of this thing. And we studied it in detail, how we can find that out. Sure, there's some in there for which we do not know for O levels, like cobalt. We don't need to know what the configuration is. For IGCSE, we might want to know the configuration of these things like indium or astatine or polonium. And for that, you just have to remember that they try to achieve the most, like their preferred numbers in the shell. So 2, 8, 18, and 32. These are the 4 preferred numbers. And that's just for IGCSE. For O levels, just remember it is 2, 8, the preferred numbers that you have in your syllabus. And you don't need to go beyond that. So 2 or 8, and that's what they try to get in each shell. And obviously, at the end of it, in the last shell, they have some numbers that are not their favorite numbers or the preferred numbers. So for example, in the case of phosphorus over here, you'll notice that the last number is 5, or in the case of oxygen, it is last number is 6, or in the case of sodium, the last number is 1. That last number is basically the group number, or it tells us about the valence shell or the valence number of electrons that they have. And it tells us about their properties. This is what makes things react more or less. This is what gives them chemical properties, the valence shell, which is why it's super important to understand it and its properties. So if you come back to this, you'll notice that there are different colors. So there are groups, there are periods, there are blocks in the periodic table. We have already talked about blocks. We don't need to know much about them in O levels or IGCSE, but we do need to know a little bit about the groups. So we'll start with the most right-hand side one, this helium, neon, and all that. These ones, helium, neon, argon, krypton, xenon, radon, and organoson that we don't really have a good sample of at the moment. And you'll notice that some of these have their MR written clearly, like helium has 4.0026 or neon is 20.180. But some of them, like radon, has the number written in parentheses, 222. In fact, when you use the periodic table that is given to you in school or in exam, you'll notice that they don't even write anything. And that is because many of these atoms are radioactive. Their nuclei or nucleus, they are unstable, so they keep on breaking. And when they break down, what happens is that they don't really have good stable isotopes. So their masses keep on changing depending on what kind of atom you have. So there isn't a final number that we have agreed upon. But for some of them, we do. Like argon is 40 for O levels or IGCSE. Although if you were to use more sophisticated instruments, you'll get 39.948. So what exactly are these things good for? So noble gases, one property that they have, which makes them so lucky in one regard, is like every other element wants to be like them. So they are the idols that every other element wants to follow, is that they have stable number of electrons in the last shell. So if I were to look at helium, it has 2. The preferred number is 2. For neon, 28. Remember 28, the preferred numbers? Then 288 for argon, 2, 8, 18, and 8. Again, remember the preferred numbers were 2, 8, 18, and 32. And you'll notice that no matter which one I pick, they have preferred number of electrons in every shell. And that is what makes them so interesting for most other elements, that they're stable. They don't need help of any other atom to achieve the preferred number. They already have that. They're born that way. So that is why we call them noble gases, which means that they will try not to react. Sure, some of them do react, but not for electronic configuration, for other reasons. Like radon does react, or xenon even reacts. But for O levels or IGCSE, we say that we'll focus on the ones that are above them, the helium, neon, and argon one, and they are very inert. These are the ones that do not react at all, and they don't need to. They don't need to have any other electrons to share or electrons to gain and all that. They don't even react with themselves. They are monoatomic, which means that they exist as single atoms. So they don't have any molecules. They have single atoms. If you were to freeze them, it will be lattice or arrangement of single atoms arranged in an order. If you were to boil it, then those atoms will be moving around, individual atoms moving around. They will not react, whether it is with themselves or with other things, which makes them really useful. Why? Because there are cases or applications where we don't want things to react. So for example, at high temperature, we don't want things to react. I am making iron, I'm converting it to steel, temperature is really high. I don't want oxygen to react with it. I don't want oxygen to rust my iron. So what will I do? I will surround it with argon. And once I do that, oxygen will have no way of coming in contact with iron or carbon that I have, even at high temperature. And my iron or carbon or steel, whatever I have, will be safe. So that is what argon is used for. Why argon? Because argon is the most abundant noble gas in the atmosphere. That's a fact that you need to know. Argon is the most abundant noble gas. So we use argon for that. We also use argon to fill light bulbs, with the incandescent bulbs that we used to have, or the ones that we now have as a novelty. Those we used to fill with argon because argon was unreactive even when the temperature of the filament reached many hundreds of degrees Celsius. Neon is also used to make lights. It glows. By the way, all the noble gases glow when you pass current through them. And we use neon in particular. And this has a very bright glow that we use. And we fill lights or tubes with neon. And then we apply current on that, and it glows, giving us different colors. Helium, we use it to fill balloons. We use it because it's light, so it goes up, but it doesn't explode because it's unreactive. So two advantages. It's light, so it goes up, it doesn't explode. We could have used hydrogen because it was light, but then hydrogen is super dangerous. It's explosive. Even though it's much, much lighter, like hydrogen is half the weight or mass of helium, but it is explosive. So we try not to use hydrogen. We prefer helium. If you want to look at how dangerous it can be, look at Hindenburg disaster. You can just Google it. All right, so that's noble gases. Three of them you need to know the uses of, and you need to know that they don't react in general. Okay, so let's look at metalloids now. These are the metalloids, and you'll notice that they make a staircase. For these, you just need to know that they are non-metals that act as metals. So they might ask you in the exam that, all right, identify a metalloid, or which of these is a metalloid, or what is a metalloid. So you just need to know that metalloids are non-metals that act like metals. Obviously, it depends on when something can actually conduct electricity, what conditions required, and there's a whole field of study that is dedicated to just these. By the way, computers, they are possible because of silicon in particular, or other compounds or mixtures made from these metalloids. So germanium plays a really important role in there, named after Germany. And we use these where we want some properties of metals, but we want some properties of non-metals as well. So they're really good for making a hybrid kind of element, you may call them. And they are useful in electronics in particular. Arsenic, another one in there, you can notice the number 33. Arsenic causes cancer. Unfortunately, Punjab has a high level of arsenic, in groundwater in many densely populated regions as well. For example, in my village, I remember that a team from UN came to survey the water, and there were only 4 houses in the whole village that did not have arsenic in their water because they had dug it really deep. But everybody else, all 5,000 or whatever houses were there, they had arsenic, and that causes cancer. So it's a hazard to have arsenic in your groundwater or whatever water you use. So it's important that you filter it and you make sure that whatever water you're using is safe for human consumption. Okay, so then we have transition metals. By the way, there are some that are post-transition metals like these, and then there's transition metals, all of them. But in O levels, we just say that, all right, all of them are transition metals. Transition metals are called transition metals because they show a change. What changes? Their oxidation state. So you'll notice that, for example, if I were to look at these electrons over here, you'll notice that lithium has a number 1 written right below it over here. Sodium has 1, potassium has 1, rubidium has 1. What does this 1 mean? It means that it has a positive 1 charge on it when it forms ion, or it has an oxidation state of 1. Similarly, if I look at fluorine over here, it has -1. If I look at chlorine, -1, bromine, -1, iodine, -1. They're all in the same group, so they make -1 charge. Okay, but it does not the case with these. With these, you can notice that, for example, chromium has 3, 6. It can also form ion of 3, which is green, and it can also form ion of 6, which I think is orange. You have manganese. It can form an ion with +2, +4, or even +7. Manganese is called the chameleon of the periodic table because it shows so many colors. Rhodium, for example, while you can see that this is 3, 3 is not the only charge that it has. Usually it forms other ones as well, but 3 is the most common one. There are 2 in particular over here which are not typical transition metals, and that you need to notice. Zinc, for example, is not a typical transition metal. It always forms +2 if it were to react. +1 does form in some cases, but in O levels or IGCSE, we don't get to that. Similarly, we have scandium over here, named after Scandinavia. Its most stable oxidation state is +3. So scandium and zinc, they are 2 transition metals that are not typical. They don't show variable oxidation states. Another thing that transition metals are good at is that they show colored compounds or colored solutions. But zinc and scandium both form either colorless solutions or white compounds, not colored compounds. So they're not traditional in that sense as well. These oxidation states do serve a purpose. We use them as catalysts, either directly or as part of a compound, because having this oxidation state means that they can play 2 different roles even in the same time. So that is why we use vanadium 5 oxide in contact process when we're making sulfur trioxide. We use iron when we're making ammonia, and that ammonia is a very useful compound. We make so many things like fertilizers, for example, from ammonia. So iron is a catalyst for that. Similarly, converting vegetable oil to margarine would be really difficult and expensive to do with a high level of efficiency if it wasn't for nickel. Nickel is the transition metal that we use as a catalyst over there. So if in our cars, we have rhodium, palladium, platinum, all 3 of them in catalytic converters when we want to make sure that the smoke that comes out of the cars doesn't really harm the environment as much. So there are others as well, but we don't need to know about them. We just need to know about nickel, manganese, chromium, vanadium, nickel, iron, vanadium 5 oxide, and rhodium, platinum. In fact, you can just skip that name. You just need to know about those. So you just need to know that they're used in catalytic converters in cars. So that is transition metals for us. Now, there are 2 chemical properties that you need to know about. One chemical property is of group 1. In group 1, what happens is that, Yeah, so in group 1, lithium, sodium, potassium, what you can notice is that first of all, as you go down, the melting point, do you see the table on the left side? Notice the melting point in there. So you can see the lithium melts at 180. Sodium, on the other hand, melts at 98. Potassium at 63. Rubidium at 39. Cesium at 28. And francium at 21, which means that francium would be a liquid at room temperature. Weird for a metal. Like we know about mercury, but because that does exist at room temperature, francium, we haven't been able to get a good enough sample of it because it's so radioactive. Yeah, so that's a trend that I wanted you to notice, that as you go down the group, melting point decreases. And why is that? That is because the metallic bonding that these have weakens. There are weaker metallic bonding, or the force of attraction gets weaker. And why is that? Let me show you another thing. So, for example, looking at lithium, do you see that radius calculated thing on the left side table? You'll notice that the radius of lithium is 167 picometers. That's a really small number, picometers. That's like a thousandth of a billionth of a meter, like really, really small. But the radius of lithium over here is 167. Now keep that number in mind. Look at sodium, 190, bigger than 167. So sodium is bigger than lithium. Look at potassium, 243, much bigger than sodium. Rubidium, 265, even bigger. Cesium, 298, so much bigger. We have almost double the size from lithium. And francium is, the radius is not known because it is unreactive. Oh, sorry, radioactive. So another trend that you can see over here is that as you go down the group, the size increases. And that is true for every group, by the way. As you go down the group, the size increases. What does it mean for metals? As metals become bigger, they obviously lose electrons faster. Why? Because the energy that they need to lose that electron is less. It is easier to lose an electron that is very far away from the nucleus compared to an electron that is closer to the nucleus. Let me show you how we can find that out. So in the table, you can see the ionization heading, if you notice. For lithium, it says 520 kilojoules per mole. So ionization means how the energy required to make ion. So for lithium, the value is 520. That means lithium to lose its last electron, it will need 520 kilojoules for 1 mole of lithium. We'll get to what mole is and all that. Just look at the number now. Ionization for sodium, 496. Lesser than that of lithium. This means that you need less energy for sodium to become an ion. No wonder sodium is a bigger atom, loses electron much easier. Potassium, 420. Rubidium, 403. Cesium, 376. So as you go down the group, atom becomes bigger. The electrons go further and further away. It becomes easier to lose them. What does it mean for the reactivity? It means the atom or the element becomes more reactive. It can make ions with less energy, which means it will react much faster than the one before it. So that is why potassium is much more reactive than sodium. They both have to lose 1 electron when they react, but potassium is bigger. It has weaker, it has like a weaker force of attraction between the last electron and the nucleus. So it can easily lose that, which is why potassium is more reactive. Sodium is less reactive. By the way, they're all very low density elements. Okay. Let me change the unit of density, gram per centimeters. So water has a density of 1 gram per centimeter cube. On the table on the left, the second last line is for density. Water has a density of 1. Sodium has a density of 0.968, which means sodium, if you put it in water, it will float because it has less density. Look at potassium, 0.856, much less than 1, which means it will also float. Rubidium, 1.53. This will actually sink. But in O levels or IGCSE, we focus on sodium and potassium. So if you look at those, or if you find these and you put them on water, they will float. So when they react, they float on water. They're very reactive. So they replace the hydrogen in water. They make sodium hydroxide. That sodium hydroxide is alkaline. So the pH of the solution increases. So not only do they float on it, they move around because they have less density, and then they form sodium hydroxide, which is very alkaline. And they replace hydrogen to do that, which means that hydrogen will start to, come out of that solution. And so hydrogen, which is explosive, as I already told you, hydrogen can catch on fire because the reactions are exothermic. So whenever you put sodium or potassium on water, you'll see that it floats. You'll see that the bubbles of hydrogen are coming out. You might see hydrogen catch fire, but definitely you will see sodium moving around, dissolving, getting smaller in size. And if you were to check this pH of the solution, you'll see that it becomes more alkaline. Now, let's identify the same trends, atoms getting bigger, density, those kind of things. But let's look at on the other extreme, over here, fluorine. So fluorine, notice that its ionization is 1681. That means that it needs 1681 kilojoules for 1 mole to react. Fluorine is 1251, less than that. Sorry, it's more less than that, yeah. Bromine, even less. That means they don't have a good, it becomes less and less for them to lose electron as you go down, right? But when it becomes difficult to lose electrons, it becomes easier to gain electron. Now look at the radius. Fluorine is 42 picometers, a really small atom. Fluorine is 79, much bigger than fluorine. Bromine is 94, even bigger. Iodine is 115, almost 3 times the size of fluorine. So what's happening here? As you go down the group, the atom becomes bigger. So bigger atoms, just like group 1, they were getting bigger. But bigger atoms find it easier to lose electrons, difficult to gain electrons. These are group 7 elements. They gain electrons better. So that is why as you go down, they become less and less reactive. So fluorine is more reactive. It gains electrons much easier, with much less energy than chlorine, which does the same thing better than bromine, but worse than fluorine. So what this means is that on both sides of the periodic table, you have opposite trends. But the reason is the same. From top to bottom, the size of the atom is increasing. It is becoming difficult to gain electron, becoming easier to lose electrons. So metals become more reactive because they have to lose electrons. And non-metals become less reactive because they have to gain electrons. Similarly, in group 7, you will notice that the density, if you look at density in the second last line on the table on the left, you'll notice that for fluorine, it's really, really low, 0.001696. But for chlorine, it's higher, 0.003. For bromine, it's even higher, much higher than actually water, 3 times that of water almost. So that means bromine will be a much more dense substance. And same for iodine, 4.94. Turns out the density increases as you go down, and not just density, the color also darkens. Fluorine is yellow, chlorine is yellow-green, bromine is red-brown, and iodine is black as a solid in room temperature and pressure. So you'll notice that at room temperature, if I look at this, iodine is solid, and so are the other things, but notice the iodine. At room temperature, bromine is liquid. At room temperature, fluorine and chlorine are gases. Although others are also highlighted, but that's important, that they are gases at room temperature. And that is because they have a very low density and they have low melting point. And why is that? Or even boiling point. Why is that? Because they have weak intermolecular forces. Because the atoms are smaller, they have weak intermolecular forces. Bigger atoms have stronger intermolecular forces for molecules, not for atoms. The metallic bonding weakens. Okay, so these are some trends that you need to know about as far as the periodic table is concerned. I've shared a modified form of periodic table with you although I would highly recommend this website, ptable.com. It has so much information on any element, and it's fun to play with these. So do give it a try to go through these isotopes or compounds. You can even just randomly pick elements, like what is the compound. If I so now when I selected magnesium, it tells me what other elements magnesium forms compounds with. So I can just say, all right, I put magnesium and sulfur here. So it has given me a list of all the other known compounds that are between magnesium and sulfur. I'm like, okay, I want to figure out for hydrogen and oxygen. So now it will tell me that there is D2OH, O2, all of them, like what state they are in. So it's a very so interesting website. So I would suggest that you go play with this website. You can also fit this form, these things. Why are they separated from the rest? Because actually this is the periodic table that you would like to study, but you can see that how long this is. So that is why we make it a shorter one by moving these downwards. That is why it's printed like that. These are also transition metals. So that is periodic table, the chapter on it. You can see that there are so many facts that you need to memorize here. So spend some time going through the syllabus, going through the notes, and also the modified periodic table that I've shared with you. So if you have any questions, feel free to ask. That's it for today.